pleasure to introduce Sarah Blunt, who's our first invited speaker and also the upcoming panelist in the next panel talk. She's a finishing PhD candidate at CalTech who will begin her postdoc in the fall as a Northwestern Sierra Fellow, and she also works at the intersection of exoplanet stars and data science. And today she's going to talk to us about some packages that you've probably heard of, Radvil and Orbitize, and her other general thoughts on open source software. So please take it away.
Thanks so much for the introduction. Share my screen. I'll get started. Okay, can you all see my slides?
Yes, we can.
Yep.
Okay, great. Yeah, so first off, thank you so much to the organizers for putting together this really fantastic conference. It's really cool to see something like this happening, and I'm really honored to be a part of it, and thanks so much for the invitation. Yeah, so today I'm going to take you through my adventures in open source software development and exoplanet orbit modeling. So this talk is structured roughly the way that my path through understanding and using open source software has happened. So the way this started off for me is that I initially learned how to code. I then spent a bunch of time learning to code well, and I've crossed out well and replaced it with mindfully, and I'll get into what I mean by that. Um, I started to then develop big projects, and from there, I worked on my first open source projects. Um, then I started developing from scratch my own open source projects, and that brings us to where I'm at today, which is using open source projects, still developing and still developing, starting to teach others, learning more, and gaining more experience outside of astronomy. Throughout this journey, I've gained a lot of confidence and developed more independence, and I've started to understand the value of using pink and purple in my plots, and you'll see that reflected as we take a chronological journey through my experiences as well. Okay, and I've got a little outline on the bottom here to sort of reflect this overall chronological path that I'm going to take you through with me today. So let's start off with my experiences learning to code. I learned to code just before I went to college. I took a year off between high school and college to, among other things, to work, and I ended up also having my first research experience in astronomy towards the end of this year. And I was really lucky to work with the BDNYC group in New York. And in particular, I got to work with the wonderful Adric Riedel, who was a postdoc in the BDNYC group at the time. And Adric taught me to code by coding through me. He would literally stand behind me and say, okay, now type this, and what do you think that's going to do? And I would guess what it would do and be wrong. And he would guess what it would do and be right, which was very amazing to me at the time. And so a couple of things about the way that I learned to code that Adric taught me, I really, really liked. One was that even from the beginning, when I had literally never run a Python or any sort of program in my life, I had a project to work towards, and something. This GIF was sort of the outcome of the project. I'll explain it more in a sec. So I had this goal that I was working towards the entire time. Adric also didn't let me flounder too much. He would give me space to try out things, but if it clearly wasn't working, he would step in and help me out. And he also debugged with me, which was really, really valuable. I got to see a real astronomer being confused by code and not knowing what to do and trying out a bunch of different things. And when I'm mentoring my own students, that's something that I think is very difficult to do. I find it very hard to debug in real time in front of other people, but I've seen how valuable it was when Adric was teaching me. And so I've really tried to do that as well. Okay, so what was this project that I was trying to do? So all of these little dots here are stars in the Beta Pictoris moving group, and the ellipse that you're seeing is the dispersion of positions at times in the past of the Beta Pictoris moving group. So essentially what Adric was trying to do through me was to project the current space velocities of the stars in the Beta Pictoris moving group back in time. So he could see when the when the distances between the stars was at a minimum, and therefore provide a clue for when the moving group would have formed when the stars were closest together. Okay, so I learned code through ADRIC. Um, the next step in my journey was learning to code well, and I initially wrote this presentation using the word well, but I decided to cross it out because first, well is relative, and I think there are a lot of people in the world that would laugh at me saying to you that I code well. And second, I don't think that's really what I meant. I learned to code thinking about how I was coding and taking time to make decisions when I was coding. So that's really what I want to sort of impart to you here. Uh, in college, I learned to code mindfully from two major sources. First was computer science classes that I took, and second was Eric Nielsen, who is currently a professor at New Mexico State. So some of the lessons I learned from the computer science classes that I took were to test everything, and this is a theme throughout this talk. In particular, my classes taught me that I should spend more time and more energy and more lines of code writing tests than I should write code. I also learned to think like a computer, and when I was debugging, to go through the code the way that the computer would, first by parsing it, then by compiling it, then by actually running it. Um, and I could find errors about it, not, well, what if this is the problem? What if this is the problem? But actually going through iteratively the way that the computer would. I also learned that I really liked coding. I had a really good time solving problems in code. And I decided from these CS classes that whatever I did with my life, I wanted to make sure that coding was a big part of it. Um, so computer science classes are very valuable, but I didn't learn from any astronomers in my computer science classes, and a lot of uh, some of the most some of the other most valuable lessons I learned in college about how to code mindfully were from Eric. And Eric taught me that writing efficient code is iterative. You have to start with the slowest part of the code and hammer away at that part, and then keep going back. Um, this is something that maybe sounds obvious when I say it like this, but um, when I was learning, I always really wanted to just work on the thing that sounded most interesting to try to improve. And Eric taught me that if you really want to make the code faster, you have to start with the part that's slowest. Um, Eric also taught me that code might run, but it also needs to be correct. And this is sort of, in my mind, an extra step in writing code when you're doing scientific programming. You first have to make it compile, then you have to make it run, and then you have to make it run right. And I've learned time and time again that just because it runs doesn't mean it's actually giving the correct result. So Eric taught me that when I'm writing code for science, I need to check and assert and validate over and over and over again at every single point I can think of, and to be constantly testing my assumptions about what I think the code is doing. Eric also taught me that I actually really like debugging, and I think this is a nice reframing from the popular sentiment about debugging, that debugging sucks and we hate it and we wish we didn't have to do it. But debugging is actually a fun challenge and problem, and I've had a lot of fun and been really excited by some of the bugs that I've worked through in my life. Okay, so the next step in my journey was developing big projects. So another amazing thing that Eric did for me was to guide me through developing my first big project, which was the Orbits for the Impatient algorithm. So I'm going to do a little bit of a detour to explain what the Orbits for the Impatient algorithm is. And just to foreshadow a little bit, this algorithm eventually became Orbitize, which I'm going to talk a lot more about later in the talk. Okay, so orbit fitting is the process of converting sky projected motions into 3D orbit posteriors. And this is specifically for directly imaged planets. Orbit fitting means different things to when you have different types of data. But for this particular process, when you have directly imaged planets, this is what we're trying to do, convert these 2D measurements into 3D posteriors. So the way that this works is you start off with raw images of an exoplanet relative to its star, and you take one of these images. You take an image, you know, periodically, and you get several different images at different points in time. And from this amazing movie that Jason Wong made, you can see the planet actually moving in its Keplerian orbit around the star at the center, which is blocked out by a coronagraph here. So you then extract measurements. Here I'm showing separation and position angle of the planet, which are polar coordinates for the position of the planet over time. And then we take these two-dimensional measurements, 2D in time, and convert those into probability distributions over orbital parameters. So there are several different orbital bases that you can use. The one that I'm showing here includes the parameters semi-major axis, the inclination, and the position angle of nodes, which are angles that orient the planet's orbit on the plane of the sky, relative to the plane of the sky. Okay, so the issue with directly imaged planets in particular is that we can only observe them over very short orbital arcs. And this is because, excuse me, this is because direct imaging is currently sensitive to planets that are very far away from their stars. And if a planet is very far away, it typically has a very long orbital period. So even if we observe it for like 10 years, which is a long time in human timescales, it's still only a fraction of the planet's orbit. And this small fraction of the orbit translates to very wide probability distributions that most algorithms struggle to compute. And this is because a lot of algorithms that are out there to compute posterior probability distributions are optimized for Gaussian posteriors. That's not true of everything, and it's definitely not. It becomes less and less true the more time goes on. But yeah, true in general. So just to hammer home this point, I'm showing again. I'm showing you a couple of sample orbits fit to some data for 51 Area B, which is a directly imaged exoplanet. So on the right here, these are 100 sky projected orbits that are drawn from the orbit posterior of this planet. And on the right here, these are the polar coordinates again. So the data is here. If you sort of zoom in very far where all of those orbits sort of converge, that's where we have the data. But you can see that there's a wide variety of exoplanet orbits that are consistent with this data. So there's still a lot of really interesting information in these orbital posteriors, and we'd still really like to know what they are, but it's difficult with conventional algorithms. So OFTI, or the orbits for the impatient algorithm, is an algorithm that was invented to address this. It's a modified rejection sampling algorithm, and it works really well for imaged planets. So let me take you through the steps of the algorithm. Just to orient you a little bit, this little cluster of black points here is data. So this is all of the data that we have for this particular exoplanet that we're trying to fit the orbit for. And the red circle here is the orbit that you want to try and fit. So rejection sampling algorithms work by drawing a random orbit or a random sample from your priors, and then rejecting or accepting that orbit based on how well it fits your data. The modified rejection sampling, the modified part of OFTI, comes in because we're not drawing just any orbit from the priors. We're only picking ones that we think have a better chance of fitting the data. And the way that we make them have a better chance is by scaling the semi-major axis and rotating the position angle of nodes. So essentially, we're just changing two of the orbital parameters so that they intersect the data better off the bat, and then we do the standard rejection sampling algorithm process. So there's this algorithm that Eric walked me through the invention and implementation of. So the original OFTI code that I wrote under Eric's supervision is a few thousand lines of IDL code. And for years, Eric and I were both the code maintainers and the only expert users. So if people wanted to use the code, they would email us and say, hey, can you run OFTI on the system? Here's the data that we have. And we'd say, sure, sounds good. We'd go do it, and we would email them posteriors or plots or both. And this was really great for my career. This got me into PhD programs, and it also got me to work on a wide variety of interesting orbit projects. But it also meant that all of the expertise on using OFTI was with me and Eric. Okay, so now I'm transitioning into developing open source projects. So this is uh, in my timeline. This is over a post-bac year that I did at CalTech. So right before I started grad school. We're taking a break from direct imaging and going into radial velocities for a bit. So over this post-bac year that I did at CalTech, I ended up over the course of the year writing the Gaussian process regression module for RadVel. And this involved a lot of firsts for me. This is my first time working with open source code. Um, I was faced with a huge pre-existing package and I had to figure out how it worked, in addition to, how to modify it or how to, yeah, that's the only word I wanted to say. Um, it was also the first time I was writing object-oriented code in Python. Um, I had some experience with Python at this point, but really didn't know how to write object-oriented code, especially in Python. So the way that I did this was I started by making a small but wide-reaching change to the API. So changed a sort of very fundamental parameter in Radvel that ended up getting propagated through the entire code. And that eventually gave me enough familiarity with the code and taught me enough about open source programming and object oriented programming in Python to eventually add this new Gaussian process module. So, Gaussian process regression is something that I think uh, probably a couple people on the call have heard of. This is a tool that allows simultaneous modeling of Keplerian orbits and correlated noise due to stellar activity. So to take you through this diagram on the right, uh, imagine that we have these purple and pink data points from two different instruments. So these are radial velocity data points measuring the speed of the star. Um, and we want to jointly model uh, the stellar activity due to rotationally modulated star spots and Keplerian orbits. So in this star, the lower frequency stuff that occurs on this sort of period is the star spots causing the stellar activity, and the higher frequency stuff that sort of goes up and down like this is the planet's orbit. Um, so with Gaussian processes, you can model both of these at the same time, and you end up getting this. The central line is the mean predicted model, and the pink and purple bars are 1 sigma uncertainties for how certain the Gaussian process model is for what the star is doing at that given time. And then on the bottom here are uncertainties. So there, I highlight this because it was an important step in my journey, but also because I've worked on this module a lot. I think this is probably the thing that I've rewritten most out of all the code that I've written in my life. It keeps changing as I learn more about how to code well, um, as I learn more about Gaussian processes and about statistics, and as I have more and more desire to make things pink and purple. And I continue to work on it. So some examples of things that I've changed to this code. I've changed the API or the way that people interact with the code. The whole structure of the code uh, I've gutted and redone many times. I've also incorporated other open source codes to actually do the guts of the Gaussian process regression calculations. Um, I've changed the statistics and the actual implementation. Um, Incorporating different assumptions or making it possible to incorporate different assumptions about Gaussian processes. So this has been a really nice sort of toolbox for me throughout my career to play around with and learn about Gaussian processes and about stellar activity through. All right, so swinging back to OFTI and the direct imaging. Developing for Radvel gave me the tools to open source the OFTI algorithm. At this time, I was still, Eric and I were still responding to emails and sending people posteriors. But I had a great conversation with Jason Wong at a conference who had a similar setup with an MCMC implementation of this orbit fitting an MCMC orbit fitting implementation. And he and I realized that we were both getting a lot more emails than we wanted about like running this code for people. And we're like, oh my God, it'll be so much less work if we just like make this code and then people will run it. But spoiler, it wasn't less work, but it was better. um, so this was the birth of Orbitize. He and I having these two different algorithms that uh, ended up with the same posteriors, but were better in different situations. So Jason and I designed Orbitize together. We actually wrote the initial code, the outline for the code at AAS Hack Day in 2019, which was super fun. And that's where we came up with the name Orbitize as well. And that's kind of a lie. We didn't come up with the name Orbitize. I actually don't know who came up with it. There was a person who I don't remember their name, but we were going around the room and like asking for names for this package, and we had like a list of 10 names or something, and this guy who I don't remember who he was, so if it was you, please tell me. He was like, all those names are kind of bad, what about like Orbitize or something? And we were like, oh yeah, that's good. So yeah, let me know who that person was. um, so yeah, so Jason and I designed the code together, and I wrote most of the initial code. We made a bunch of choices in version one of the code that I think were helpful for it long term. Um, First, the original motivation for writing this code in the first place was to have this API to support multiple backend algorithms. So we wanted users to easily be able to go back and forth between Jason's MCMC implementation and my OFTI implementation. We also focused only on relative astrometry. So there were other types of data that we wanted to incorporate in the longer term, but we were focusing initially on just making it work for one type of data. Uh, we also spent a huge amount of time writing great docs, great tests, and great tutorials, and that paid dividends in the long term. And we chose a purple logo, and we made a meme page at the same time together. So as good as having the OFTI algorithm was for my career, open sourcing OFTI was even better for my career. It was extremely helpful. It gave me a lot of publicity, and I think overall it was just a really good decision. I'm very glad that we open sourced it. So I then quickly became an expert user of Orbitize through this project that I worked on with Brendan Bowler. And this is sort of a point that's worth emphasizing. I think that I initially thought that being a developer of a code would automatically make me an expert user, but that's definitely not true. It took me a while to still become an expert user of this code that I had written. Um, so yeah, but so having a project to work on, a scientific project to work on, was extremely helpful for that process. So I, I did this. I became this expert user to understand the eccentricity distributions of image brown dwarfs and planets. So this is something that yeah, so this diagram is showing on the right here, these are the posterior distributions over the population level eccentricity distributions of giant planets and brown dwarfs. And you can see that brown dwarfs have this wider eccentricity distribution, more uniform over different eccentricities, whereas giant planets have primarily lower eccentricities. And so we took this as evidence that these two populations of objects form differently. So if you look on the left part of the plot, you can see uncertainties in eccentricity and mass for a bunch of individual objects. So each one of these was an orbit fit that I ran with Orbitize, and each one had its own idiosyncrasies and bugs that I had to figure out. I had to, assess MCMC convergence. I had to decide when to use MCMC or when to use OFTI. And yeah, I found lots and lots of different bugs in Orbitize doing this. So this made the code, I think, really robust. The fact that we had to do all of these orbit fits and make sure that each one of them was working. All right, so let's go back to the timeline. To review, I told you about how I learned to code, how I learned to code mindfully, developing big projects, in particular, writing the OFTI algorithm, working on open source projects. Radvel in particular was really helpful for my development, and then developing my first big open source projects, i.e. Orbitize. So now I'm here. I spend a lot of time using open source projects, and I'm also spending a lot of time teaching others. So I wanted to briefly talk about some lessons that I've learned since Orbitize version 1. Uh, one important lesson is one important suggestion that I can make to everyone is to develop for yourself and for the science that you're interested in. Um, Pretty rapidly, people started asking me to make changes to the code and had suggestions for what they wanted to see, which was really great to hear. But it was also overwhelming. And I eventually realized that I couldn't just develop for other people and that I wanted to make sure that I was doing my own science first and making changes to Orbitize that were helpful for me in my science. And that ended up being helpful for other people as well. Um, I'd also encourage everyone to keep starting new projects. This, I, uh, I also thought that for a while that because I had this big code, I wasn't able to start new projects and that I had to just spend all my energy maintaining this current project. But there's a certain type of learning that comes from starting something new and designing new code. And I think it was very important for me to continue doing that. Um, yeah, another thing that I've said before is that making docs tutorials and tests really good is super impactful and very helpful. Uh, and yeah, own your work, and we don't need the haters; we can ignore them. All right, so now for a series of a couple of advertisements, I guess. This summer I did an internship at Google, and I wanted to briefly talk about some lessons that I learned and maybe sort of start some conversations based on some of the practices that I saw there. Um, One thing that was emphasized from the get-go at Google was code standardization. So they really cared about things like PEP 8 compliance, like making sure that your code followed all of the regulations. So making sure that nothing was over 80 characters, no line was over 80 characters, and exact number of spaces and things like that. And initially, it seemed really annoying, and I was like, well, why do we care? But it made code really easy to read and really easy to port from place to place. And this is something that I don't think we've thought about a lot in astronomy. We just sort of assume that everyone has their own coding style, and not everyone is going to, want to standardize. But I think it was actually very valuable and saved a lot of time. So I think this is something we could talk more about as a community. Um, Another thing that uh, I was sort of surprised by was that people at Google reviewed every single line of code. Multiple people reviewed every single line of code. And I think this is something we're starting to do more as an astronomy community, but I think is worth pushing for even harder. Um, we, I am realizing as I it's becoming more standard practice to submit a GitHub notebook, for example, or sorry, not a Jupyter notebook with papers. Um, but we don't necessarily review those lines of code. We have this thought that once you get to be a good enough coder, your advisor or whatever is not going to review your code anymore and look at every single line. But I think that would save a lot of time and mistakes. So yeah, I think that's something that's potentially worth discussing as well. And again, the importance of testing. Um, yeah, and Googlers call their dogs Dougalers, which is very bad. Okay. All right, last advertisement. I want to briefly talk about the present Code Astro, which is a week-long hybrid workshop on developing open source software for astronomers that Jason and I run together. So Code Astro has this is the fourth year we're going to be doing it this year, and we teach folks sort of best open source coding practices from from GitHub and docs and testing and all sorts of stuff, and it's a really great time. And yeah, this has been a really great opportunity for me to sort of tying back to the beginning of the presentation, when I was learning to code and learning to code well and mindfully, this has been a really good opportunity for me to try to teach that and pass that on to others. Yeah, and I will leave up my final thoughts. And yeah, thank you so much again for the invitation and for your time.
All right, let's thank Sarah Blunt. What a fantastic intro or talk and intro to, or segue into our panel discussion.